The second part of our unit on atoms, molecules, and ions will look at naming and formula writing for chemical compounds. Chemists needed a system for naming compounds in which the name tells us something about the composition of the compound. We will first focus on binary compounds, which are made of two elements bonded together. There are binary ionic compounds, which is a metal bonded to a nonmetal, and then binary covalent compounds in which two or more nonmetals are bonded together. The first type of ionic compounds is made from a cation and an anion. The cation is always named first and the anion or negative ion second. The cation always has the same name as the original element. For example, we call Na+ a sodium ion. For the anion, we change the ending of the element to "ide," so the chlorine atom becomes the chloride ion. So let's look at some examples of binary ionic compounds type 1. Letter A would be called cesium fluoride, letter B, aluminum chloride, and letter C, lithium hydride. Formula writing, we need to first find the charge of each of the ions in the compound and then write a formula in which the compound is neutral. So, for example, potassium iodide. Potassium is in group 1 and carries a +1 charge. Iodine is in group 7 and has a -1 charge. Since these ions have the same charge but opposite in sign, we just need one of each to form a neutral compound. Therefore, the formula is Ki. Calcium oxide, calcium is in group 2 and always has a 2+ charge. Oxygen is in group 6 and has a -2 charge. Again, since the charges are the same, these two ions will form a neutral compound in a 1-to-1 ratio, and the formula is CaO. Gallium is in group 3 and has a +3 charge. Bromine is in group 7 and has a -1 charge. This time the ions do not possess the same charge, so we need to determine how many of each we need to form a neutral compound. In this case, we would need 3 bromines to balance the charge of the gallium. Therefore, the formula is GaBr3. There's a second type of ionic compound that we can name, which contains transition metals. Transition metals tend to form more than one type of positive ion. Because of this, we must specify the charge on the ion, and we use Roman numerals to indicate the charge of the cation. With chemistry, there are always exceptions to every rule. Silver, zinc, and cadmium are all transition metals. However, they do not form ions with multiple charges. Silver is always +1, zinc is always +2, and cadmium is always +2. Therefore, we do not use Roman numerals when naming compounds containing these ions. On the other hand, lead and tin are not transition metals. However, they can form multiple ions. So we must include Roman numerals to communicate whether it's the +2 or +4 ion in the compound. So let's look at some examples containing transition metals. For CuCl, copper is a transition metal, so it can have various charges. So we're not sure what the charge is. Chlorine, however, is in group 7 and will always have a -1 charge. From the formula, we see these ions combine in a 1-to-1 ratio, so we can deduce the copper must have a +1 charge in order to neutralize the -1 of the chlorine. We communicate this again with a Roman numeral, and this compound would be called copper-1 chloride. For the second example, mercury is again a transition metal, so we don't know the charge, and oxygen, which is in group 6, always has a -2 charge. Again, since they are combined in a 1-to-1 ratio, the charge on the mercury must be +2, and this compound would be called mercury-2 oxide. The last example, again, iron is a transition metal, so we're not sure of the charge, and oxygen always has a -2 charge. Due to the fact that there are 2 irons combined for every 3 oxygens, we can deduce that the charge on the iron must be +3, and we would call this compound iron 3 oxide. Now writing the formula will be exactly the same, but we're going to use the Roman numeral to tell us the charge. For manganese 4 oxide, manganese is +4 and oxygen is always -2. We will need 2 oxygens to balance the manganese, and the formula is MnO2. For lead 2 chloride, the lead has a +2 charge. Chlorine is always -1. So again, we will need 2 chlorines to balance the lead. This flow chart can be used when you're naming type 1 or type 2 ionic compounds. Again, if the element or if the compound contains a cation that does not have multiple charges, then you just name the cation. However, if it is a transition metal or tin or lead, we must use the principle of charge to determine the charge on the cation and indicate it with a Roman numeral. All right, we have a couple mixed together of the 2 types. So cobalt and bromine. Cobalt is a transition metal, so it can have multiple charges, and so we must include a Roman numeral. We can see that there are 2 -1 bromine ions to balance the cobalt, so it must be a +2 charge, and this would be called cobalt 2 bromide. For calcium chloride, calcium is an alkaline earth metal. It only forms 1 type of ion with a +2 charge. Therefore, we don't need a Roman numeral, and this would be calcium chloride. Aluminum is also not a transition metal. It only forms a +3 charge, and so a Roman numeral is not necessary when naming. Okay, a couple formula writing examples. Chromium 3 chloride. The Roman numeral 3 tells us the chromium has a +3 charge, and since chlorine has a -1 charge, we need 3 chlorines to balance the chromium, and the formula would be CrCl3. Gallium has a +3 charge based on its position in the periodic table, so we need 3 -1 iodine ions to balance this charge, and the formula is GaI3. The next section on naming has to do with polyatomic ions, which I also call polys, and it's an ion that is made of more than 1 atom. They are assigned names that must be quote-unquote memorized. This is a list of the most common polyatomic ions, and many of these should be familiar to you. I will point out that within the polys there are oxyanions that contain a certain element and then a different number of oxygen atoms. And there's a couple of tricks as far as naming these polys. When there are 2 polys in the series, the poly with the smaller number of oxygen atoms is going to end in "ite," and the poly with the larger number of oxygen atoms ends with "ate." So for example, SO3, which has fewer oxygens, is called sulfite. SO4, which has greater number of oxygens, is called sulfate. Another trick with the oxyanions, when there's more than 2 in the series, we use the prefix hypo for the poly with the fewest number of oxygens, and the prefix per for the one with the most oxygen atoms. So there are 4 polys in the series containing chlorine. ClO4 is called perchlorate because it has the most oxygens. ClO3 is chlorate. ClO2 is chlorite. And then ClO with the fewest oxygens is hypochlorite. So let's try doing some naming with the polys. The first example, sodium is not a transition metal, so it only has 1 charge. And then the group SO4 from the table is called sulfate. So the name of this compound would be sodium sulfate. The second example, manganese is a transition metal that can have more than 1 charge. So we do have to include the Roman numeral. There are two hydroxide ions in the compound, which each have a -1 charge. So the manganese must have a +2 charge. And so this would be manganese 2 hydroxide. All right, now we're going to do some formula writing. Lithium always has a +1 charge, and the carbonate has a -2 charge. In order to balance the compound, we will need 2 lithiums for every 1 carbonate. Calcium always has a +2 charge. From the table, the phosphate ion, the group, has a -3 charge. I teach my students in the first year a trick. If you crisscross the charges or swap them, it tells you the number of each ion you will need. So in this case, we will need 3 calciums and 2 phosphates to balance the compound. And you may remember when you need more than one of a poly or this group of atoms, it needs to be placed in parentheses. So the formula would be Ca3 and then 2 phosphate ions. The final type of naming is with covalent compounds, which again is where we share electrons between 2 or more nonmetals. We name the first element. The second element is again going to change the ending to "ide," but this time we're going to use prefixes to communicate how many atoms are present in the compound. There is one exception. We do not use the prefix mono when naming the first element. So these are the common prefixes used to indicate the number of atoms. You'll want to review those as you begin practicing naming covalent compounds. So let's look at some examples. PCl5, there's 1 phosphorus, but again, we do not include mono. The prefix for 5 is penta, so this would be phosphorus pentachloride. Letter B, very similar, except the prefix for 3 is tri, so this would be phosphorus trichloride. And then letter C, there is 1 sulfur and 2 oxygens. The prefix for oxygen is di, so sulfur dioxide. As far as formulas, sulfur hexafluoride, just the sulfur tells us there's 1, and then hexa, that prefix means 6, so it would be SF6. Di-nitrogen is 2 nitrogens. Monoxide, mono means 1, so N2O. And then sulfur tetrachloride, the prefix tetra means 4, so it would be SCl4. So if we put this all together, we have this flow chart to help with naming again. First, you want to look to see if the compound contains a metal. If it does not, that means it's a covalent compound and you just use the prefixes. If it does include a metal, then we need to decide if the metal forms only one type of cation. If it does, then you're going to just name the element. But if it can form more than one cation, we must determine the charge and use the Roman numeral system. All right, putting everything together, P4O10, phosphorus is a nonmetal, which tells me this is a covalent compound, which means we need to use prefixes. The prefix for 4 is tetra, the prefix for 10 is deca, so this would be tetraphosphorus decoxide. Neobidium is a transition metal, which means we need to determine the charge and include a Roman numeral. Since the charge on oxygen is always -2, that means that to balance those 5 oxygens, each neobidium must have a charge of 5. So it's neobium 5 oxide. The last one, titanium, is also a transition metal, and it does include a poly, so we need a Roman numeral. NO3 is nitrate, which has a -1 charge, and since there are 4 of them, the charge on the titanium must be +4, so this would be titanium 4 nitrate. Writing the formulas, the first one, the vanadium has a charge of +5 based on the Roman numeral. Fluorine is always -1, so we need 5 fluorines to balance the vanadium. Dioxygen difluoride, this is a covalent compound, and the prefix communicates there's 2 of each atom, so it would be O2F2. Gallium is a traditional cation with only 1 charge, and it has a +3 charge to oxygen's -2, so we would need 2 galliums to balance the 3 oxygens.